Coming up in this episode of Coffee Literature Review, we go over how to make the best pour over coffee according to physicists out of the University of Pennsylvania.
Full of grift, it's full of nonsense, there's a bunch of anti-science going on here. It's just a big hullabaloo.
We're back with season 2 of Coffee Literature Review, produced by Doran Pennington, also co-hosted by Doran Pennington. I'm Chris Hendon. This year we're going to try a couple of new things. First, and probably most importantly, since the last episode, I've become a dad. And technically I'm on leave, which means I'm not on leave, I'm working, I just have a baby with me. And so today we're recording, and my baby William is here in the room, and you might hear him in the background getting upset, screaming, who knows? We're going to see how this goes. Second thing, there's been a pretty major shakeup in American science. I'm not going to talk much about that today, but it will be a topic that will come up with some of the scientific articles that we're going to be discussing with various guests. On that point, this year we're going to try and incorporate more of the scientists who actually did the work as our guests. I think one of the things that people want to hear more of is us talking to the scientists at a relatively high fidelity, when necessary, criticizing one another. It's important to see where the extent or the limits of the articles are, and the best person to talk to about that is someone who wrote it. With that in mind, we thought we'd kick off this with a very popular and pertinent article. It's just done the media rounds, published in the Physics of Fluids. The title of the article is Pour Over Coffee, Mixing by a Water Jet Impinging on a Granular Bed with Avalanche Dynamics. This article was written by Ernest Park, Margot Young, and Arnold Mathijssen. We're lucky enough to have Arnold speaking with us. He's an assistant professor of physics at the University of Pennsylvania. Thank you very much, Arnold, for joining.
Oh, excellent. How are you doing?
Yeah, good, very good. I've got my son with me. He's here. He's almost 13 weeks old, and he's
Oh, wow. I
yeah,
see.
he's small. Yeah. Hey, so first couple of things. But I wanted to get your background here. So you did a PhD at Oxford in the UK,
Yeah, that's right.
and then you moved to Stanford for a postdoc, which is kind of like a higher profile version of what I did. So so tell us about the Oxford PhD. How was it?
Oh, yeah. So I worked with Julia Yeomans there, which was really a pleasure. It's in the sub-department of theoretical physics. So the
Uh-huh.
physics building there has like a separate building for theory. But actually, they're very, very well connected with experimental physics and experimental chemistry as well.
Right.
So yeah, I started working on hydrodynamics, and then yeah, I started doing some little experiments, towards the end of my third year, and then I yeah realized that I wanted to do more experimental work, and so my postdoc then with Manu, yeah, was in bioengineering.
Some of your papers involve swimmers, which is something that the audience here probably has no idea what a swimmer is to a physicist. But I am familiar with swimmers because it was one of the first things that I was also interested in modeling, and it got me interested in coffee particles as well. So tell us a little bit about what a swimmer is and what you've studied it for.
Sure. So yeah, I mean, I like swimming myself, and I go to the pool often. But my research interest is swimmers at a much smaller scale. Yeah, so micro swimmers could be anything like bacteria or microalgae, things that swim at very small length scales. And they're important for many different things. So we're interested in bacterial infection dynamics, how bacteria can invade tissues in the body, or how we can prevent doing that using bioengineering techniques.
What allows these bacteria to swim?
Right, so they're single cells and they have flagella. So they're effectively little helical filaments. They rotate very quickly, more than 100 revolutions per second. So they go really very fast. And these bacteria, when you look at them under the microscope, they literally just zip across, they can swim like 100 body lengths per second. So it's really hard to follow one. And so it's a real challenge for us to study invasion dynamics because you need like a super fast camera and a really good microscope. But yeah, with the modern microscopy techniques, yeah, this is now possible.
Yeah, I see. And you had a paper on E. coli swimming pretty recently, right?
Yeah, that's right. Yeah, we're interested in how they can invade in structured environments. So if you have a little tube, then you can have a flow that you push from the left to the right, for example, and then you can look at how bacteria swim upstream, how they reorient against flows, and then they can contaminate these upstream areas. Yeah, and this is very important for bladder infections, for example, because then you
Yeah,
have
yeah.
flow clearly going down and then bacteria working their way up.
Yeah, sure. And so it would be fair to say then that the sort of physics that you're thinking about is at a length scale that is tangible to the human, as opposed to some of this like subatomic stuff that you see in the in your department.
Right, exactly. That's right.
So when you were hired at UPenn, they they were looking for someone who did what? Physics of real life?
Yeah, we have a special center here at UPenn that is called the Center for Soft and Living Matter Physics. And so we're basically interested in the fundamental physical mechanisms of life itself, how we can yeah, understand biological processes better using the laws of physics, but also the other way around, how we can learn from biology to make better physical devices, to make better like engineering applications by learning things from biology.
Yeah, thinking about how you might like design a designer cell that could swim in a particular way to deliver a payload of medicine or something, right?
Yeah, that's right. People are interested in making these micro robots that could, for example, swim through, yeah, the cardiovascular system and then deliver some kind of drug. And so, yeah, if we can make a little micro robot that can swim by itself, that has its own engine, that has its own navigation system, yeah, that's something we cannot do at the moment, right? And these little cells, they're very good at it. So yeah, they're very simple and small, but they can do things that we can only imagine ourselves at the moment.
So it might be a question of relativity here, but in some sense, you don't really have a coffee particle swimming when you pour water over a bed of coffee. But if you were watching where the particle was relative to the stream of water, you could think of it as basically swimming through that water, although it's not moving itself. I think much of the physics probably is the same, at least at that interface, right?
Yeah, that's what we always like to do, to find patterns or to find things that are universal, that are true, regardless of whether it's a living cell or a little particle. And so when we think about hydrodynamics, then we have an equation that's called the Navier-Stokes equation
Mhm.
that in principles describes all of hydrodynamics, going all the way from large hurricanes and weather phenomena all the way down to micro hydrodynamics of yeah, the fluid mechanics of how these little cells are swimming around.
Yeah, yeah.
And so you can imagine that yeah, depending on the parameters like viscosity, yeah, these flows are completely different. And so what we try to do is to make connections between these different systems and that we can try to find universality.
Yeah, sure. I mean, it's of course the equations get extremely complicated when you try and understand the interface of liquids with solids and add motion.
Mhm.
It's like almost an unsolvable problem. I mean, you actually do a good job of discussing that in the paper we're going to discuss today, but it's a complicated thing, right?
Yeah, that's right. So when you have a small microparticle, then there are some known exact solutions.
Right.
And most famously is the Stokes solution. So that's if you have a small spherical particle that's sinking down through a liquid, then you can calculate exactly how fast that particle is going to sink if you know its size and if you know the viscosity of the liquid. And so you can flip this problem inside out. That is, if you know its size and you can measure how fast it's sinking, then you can infer what the viscosity of this liquid must have been.
Yeah.
And so, yeah, that's often the thing you do in science. That if you can work out a problem from A to B, then you can also infer back from B to A.
We'll get to the paper here because the coffee industry is a subset of food science, and within that space, obviously, there's a really large market for high quality science. It's basically you read the literature. There's not a lot of really basic research there. There's a lot of applied stuff like, hey, if we change this variable, then we taste this thing or whatever. But we don't really have this like basic understanding of some of the most fundamental concepts in brewing coffee. And when I entered the field, I came totally from a different discipline. Like I was trained in classical chemistry, so entering and trying to think about how electrostatics impact extraction. In your case, are you a coffee guy? Like what's the deal here?
Oh, definitely. Yeah, I drink a lot of coffee actually. Yeah, I have a mocha pot at home, and I like a French press and pour over as well, of course.
So you had a general interest in coffee, but weren't necessarily academically aligning with coffee in particular.
Initially, no. I mean, most of our work is in biological physics,
Right.
but then in the lab we have a little coffee table, and that's where we just have conversations with each other, where we
Yeah.
discuss collaborations and just, projects with all the different students. Um, but we do have a lab notebook that sits next to the coffee machine. And you're always trying to improve your coffee a little bit, I guess. And so people take notes, and it's like, okay, this time we tried so many grams, and then it tastes a little better. And initially, this is just having fun, but then at some point you start seeing patterns,
Yeah.
and then you know that you're onto something, and then it's worth doing some more systematic experiments.
So the paper that I've got you on here to talk about is an article that came out very recently. This article is part of a special issue which focuses on kitchen flows. Is it fair to say this article received the most popular media that you've had in your career?
Yeah, I think it's fair to say that we were totally overwhelmed by by all of this media attention, and yeah, I had never seen anything like it.
Yeah.
Uh, and so it's been a huge pleasure, of course, but also yeah, a great learning experience for myself and for our students. And yeah, just speaking with so many people,
Yeah.
not just, in physics, but literally on the street, and people you encounter saying like, "Hey, I saw this thing about pour over coffee." It's just so nice that the community has been so welcoming.
Yeah.
And yeah, of course, like there are so many new ideas and suggestions for future research as well, which is why we're talking today. And yeah, so just a big thank you to everyone who's interested, and for being so constructive.
One of the things I've learned over the years with doing this media stuff is that you get a really strong media response if the science doesn't just tell you something that's generally interesting. Like if you wrote a paper that had no useful information in it, but it was about coffee, it would still go in the media. But if you can write a paper that is about coffee and there's like a thing to do, that will change your morning routine in some way, then it's going to go really strong in the media because then it's like not only the nerds that are interested, but also like your mom and dad might actually do something with this piece of information, and so it ends up it ends up all over the place. I saw the article first in the journal Physics of Fluids, and then I saw it in Perfect Daily Grind and CNN and all the different locations that it was being covered by the media, which is great for you. The coffee community has had a taste of this type of physics before because, of course, Jonathan Gagne's book, The Physics of Filter Coffee, discusses some of the concepts that you're talking about in here. So explain to me what is known, what is not known about pour over coffee.
Right. Yeah. So the angle that we're coming from is from fluid mechanics, and initially this really just started off as a problem looking at how yeah, small particles interact with each other when they come into contact with what we call liquid jet. And so there's been a lot of research on what's called granular flows, so particles yeah, that will have avalanche dynamics, things like snow dynamics, or granular media like sand grains, or there's been papers even on, for example, in food science, right? You have a hopper where you have rice or you have oats or cereal, that are in principle solid particles, but they can behave like a liquid. So these granular materials can yeah, have fluid-like properties. And on the other hand, there's been a lot of research in terms of liquid jets, so strong streams of liquid that will impact onto a water-air interface, for example. but these two things together, granular materials and liquid jets together, had not really been studied before. And this is exactly what a pour over coffee is. And so we thought, okay, maybe we should look at this a little bit more systematically. And the main idea is when you make a pour over coffee, that you're trying to extract some of these nice molecules that are sitting inside these coffee grounds and then mix it up into something that's a very nice drink, right? But how does that physics come in? And yeah, that's yeah the main purpose of this study, I guess.
I mean, the first question that comes up is, or at least I'd say, first thing that you discuss is the necessity for a bloom. Now, we're going to get to the silica stuff in a minute, but I just want to talk about the bloom to start because uh,
Hmm.
the blooming is this artisanal component in the coffee industry. You know, people have their different opinions about how long to bloom for and the purpose of the bloom. And this paper actually, I wouldn't say makes a firm statement about what the bloom does, but you do make a statement about what the bloom does. So I'm curious, in your mind, what is the purpose of the bloom?
Yeah, that's a great question. So there's a lot of CO2 that's trapped in coffee, and when you roast it, then yeah, you get these yeah, basically little gas that's available to be released into the coffee. Um, and so the moment you pour water over it, this gas wants to go somewhere, right? And so that's what you see. That's what this blooming phase is. That you see all these little micro bubbles that come up. CO2 is by itself acidic, and so I think this is maybe one element that could be important, right? That you could get rid of this acidity a little bit. Um, and maybe it's also something that helps with like making the ground more available to mixing afterwards. If you get rid of these little gas bubbles first, then you have more contact between the grounds and the coffee afterwards.
Yeah, sure. Rightly so, that like the rate limiting step in coffee extraction is intraparticle diffusion of material from the inside of the coffee to the outside of the coffee and
Hmm.
giving the particle time to heat up. Even though it's a evolving CO2, giving it time to heat up is also a good thing because you want to promote that. That's, I mean, that is after all the that's the reaction you're trying to do is to move material from inside to outside, right?
Yeah, exactly.
Yeah. The majority of the paper is trying to deal with this open question of like if the water hits this bed, this particle bed, the granular bed,
Hmm.
there is going to be a lot of different things that could possibly happen. Like, you know, in the layman's terms, if you pour gently, then in principle, you could float the water on top of the bed, assuming the bed has infinite density so that the water did not damage the surface and it just floated. That's one thing that could happen. But if the bed's porous, then the water can flow through. And
Hmm.
if you pour with, you know, with some degree of force, you might actually start disrupting the surface.
Yeah, right. From a fluid mechanics point of view, the liquid is trying to follow the path of least resistance. And so if you have a pour over cone that has like these little ridges on the inside, then there's basically a lot of space between the filter and the outer wall. And so if you were to pour, let's say hypothetically, extremely slowly, then the water would just sit on top of the coffee bed, wouldn't go through, but instead goes straight through the filter on the side and then run off along the side down between that little space between the filter and the cone, and then it wouldn't see any coffee particles at all. This is an
Right.
extreme case, of course, but you know,
But don't they design the V60 to have exactly that? Like the Hario V60 has those ribs.
yeah. So I think it's there to maybe promote drainage, which is maybe I don't know, yeah, could be good because you don't want the things to clog, right? So most likely you're not going to be in this extreme limit, and you're going to pour a little bit faster, and then you don't want this coffee to this liquid to sit there forever because then you get over extraction. So I think that's they probably have that designed so that you don't get over extraction in the limit that you pour faster. But yeah, there is a there is a big spectrum in terms of like pouring speeds, pour heights that we discuss in the paper. And then it very, very much depends on the size of the coffee particles as well.
Right. So the first experiment you might do then is avoid this, let's say, these highways, these ribs that allow
Hmm.
water to move not through the bed but around it.
Hmm.
And then you basically end up with just a cone. And then if you fill that cone with coffee, sure, you can do that. That's just making a pour over. But first, you want to simulate coffee because why? There's a lot of problems with coffee, but why do you go silica first?
Yes, I mean coffee is not transparent in itself, right? It's a dark fluid, and so if you want to see what's happening inside, then you better work with an optical system that has some transparency, and that's why we've replaced in in the first instance these coffee particles with these so-called silica gel particles, because they're more or less transparent when you put them in water. And so you can then illuminate them with a laser sheet from the side, and then you can measure the flows that are happening inside your coffee cone.
One of the critical observations early on is that if you pour at relatively low height, so I don't know, let's say 2.5 centimeters, very, very close to the bed
Hmm.
of silica,
Hmm.
you basically don't really disrupt the surface of silica that much. Is that right?
Yeah, that's right. So these particles will just sink down rather quickly. And so they'd much rather just form a closed bed of like very tightly packed particles. And so then you don't get any mixing at all.
The bed of silica that you're using is roughly the same size. It's supporting information figures for those following along. It's roughly the
Hmm.
same size as that of ground coffee. And so, one of the things that you definitely observe, figure two in your paper, is like coffee, the silica beads float, some of them, right? You get a crust.
Hmm. Yeah, that's right. So you can also have air bubbles that will stick to some of the coffee particles. And so that forms kind of a raft, a floating raft that sits on the water-air interface.
Yeah.
And so there is a small fraction of particles at the top. And then you have the majority of the coffee grounds that will be submersed, that will be down at the bottom of the cone.
But interestingly, those floaters there, those guys are not coming from the silica evolving CO2. Like in the coffee industry, most people think of the floating particles as those that are buoyant because of CO2.
Hmm.
Why are these ones floating?
Well, we have surface tension as well. So these particles are so small that I mean, we've all seen a picture of like a paperclip floating on water or something. And so if yeah, anything that's smaller than about a millimeter in size could happily float on water, even if it's more dense.
Yeah, I see. So it's just a little bit of agitation coming from the water stream that's hitting the surface causes some to lift
Yeah,
and
that's
form the
right.
raft. Yeah.
Exactly.
The extent to which the surface is agitated depends on what?
Uh, so first of all, the amount of energy that you put in, right? So you have you can pour this jet of water from a certain height, and so the more the more you lift up your kettle, you get more potential energy that comes down. So this jet that's going to hit the surface has more momentum. Yeah, and that's like a crucial factor for the mixing here.
So I would imagine though that if I poured this kettle from I don't know some height, at some point that water is going to reach its terminal velocity, right?
Hmm.
There's an upper limit for how much that jet, the force that jet can exert upon the thing that it's about to hit. Uh,
Yeah, I don't think you would ever reach terminal velocity in like reasonable scales in
how
this
high? Yeah,
experiment.
how high do I have to hold the kettle to hit that? Like two stories?
So yeah, I think yeah, terminal velocity means that they have a balance between the gravitational forces and the drag force.
Yeah.
The drag force between water and air is not that strong unless you have very small droplets that have, a lot of surface area, and then your drag goes up. But that's exactly the kind of parameter space that we want to avoid.
Yeah,
We,
exactly.
we don't want the stream to break up into small droplets.
Yeah, yeah. Okay, so I'm not going to try and hit my V60 cone from the top of my four-story building here.
That's right,
Okay,
exactly.
yeah.
Although it would be a fun experiment.
Yeah, I mean, maybe you should do it. It sounds like one of those things where it's like, who can get the most water into the cone? Because that'd be extremely challenging, I think.
Yeah, exactly. Yeah, that would be a good fluid mechanics exercise because then you get like wind and
Yeah,
everything.
wind is yeah, it'd be yeah, it sounds like something physicists could enjoy over over in your department for a long time. All right, so in the paper, one of the critical things is also flow rate. How much water are you pouring per second? And the
That's
range that
right.
you looked at is like 15 grams per second down to 5 grams per second. And to put us in the same sort of to plant a flag, my fellow kettle, the gooseneck produced by fellow, pours at exactly 10 grams per second at when I fully let it go. It's at 10. So
Yeah.
so
hmm
somewhere 15 is like I'd say pretty fast. But I think the fellow is actually kind of slow. 5 is slow.
Yeah. So basically you have like a fixed amount of liquid in your coffee cup, right? Let's say like maybe 300 milliliters or so. And so if you're going to have a flow rate that's 10 grams per second, you're going to have 300 by 10 is 30 seconds.
Yeah.
That's pretty fast still. So like of course it will take a bit more time for this liquid to actually drain through the coffee itself. And so then you're going to end up with maybe a minute and a half or so. And I think that's more or less the number we're looking for. So
Yeah, yeah,
something like
right.
around, a minute or two.
Something realistic, I suppose. Yeah.
Yeah,
So,
exactly. Yeah.
okay, so
But
so
then
there's
if you
two.
have like a, let's say not a gooseneck kettle, but something with a normal spout, it's very easy to just pour like 100 milliliters per second. And then, yeah, you're clearly going to flush that thing too fast. And then, yeah, that's what we want to avoid.
Yeah, that yeah. There are two more things we have to discuss briefly before we get into the sort of the key findings. So first one is we also are defining the extraction based on the concentration of coffee material that ends up in the cup. So that we call this percent TDS. The way you've defined it here would indicate that you've collected TDS based on dehydrating the coffee after you've brewed it. Is that right?
That's correct, exactly. So you make a coffee, then you evaporate all the liquid off, and you look at how many solids remain.
Yeah. Yeah, that's a very effective way to do it. I mean, the cynical coffee person might say, well, you've lost the volatile, so that's not all of the mass. And the response to that is, yeah, sure. So the TDS measured here is the sort of the lower limit of what was extracted, right? And there's all this other stuff that might have composed maybe another additional 1% of the mass or something. Who knows, right?
Right,
But
exactly.
that's not a big deal. I guess the
Yeah, there
other
are actually quite a lot of nice studies in this area. And so, yeah, you could argue that there is even some, let's say, debate in the community itself. I mean, the papers that we've read and the papers that we then also reference in our paper is that, TDS is like, let's say, the first approximation, right? That there is a very nice correlation between TDS and, let's say, the strength of your coffee cup. Then obviously, if you want to talk about flavor, then it's much more about the relative concentrations of different compounds.
right,
And
right.
so
Yeah, it gets complicated there.
that's another measurement that you could do. That's
Yeah.
right.
So the other thing we need to briefly discuss here, as probably the more physicsy component of this, is that in section B of the paper, you do a dimensionless number analysis. Solving for things like the Reynolds number is useful because it tells you which fluid dynamic regime you're operating in.
Right. So if you have a Reynolds number that is 10 to the 5, then that means that the overall liquid in your cup or the overall liquid in your pour over is going to be turbulent. However, that doesn't mean necessarily that the fluid mechanics that's relevant for the extraction is also turbulence. And so that's one of the points that we're trying to make here, that we get very different levels of extraction, which are all at very, very high Reynolds numbers.
Mm-hmm.
So it's not really the turbulence of the liquids itself that's going to help with the extraction here, but it's those little streamlines that are wrapping around these tiny coffee particles. Those are the little flows that are going to help with pulling those molecules out of the particles.
Mm-hmm.
And because these particles are so small, then locally these streamlines are not going to be turbulent. They're going to be very nice and laminar.
Right, exactly.
And so yeah, that is a much more relevant yeah physics in that case. I could also just give you a little example or a little experiment that you can try at home. So let's say that you take a spoon of sugar or a spoon of salt, and you want to dissolve this just in a cup of water. Then you'll see that it actually takes, about 30 seconds or so of stirring before all of the sugar is dissolved.
Hmm.
Uh, and if you were to do the same thing with, let's say, a drop of food coloring or ink or something, it's only going to take 1 second before, that's like perfectly mixed. And so that process of dissolution, therefore, is like not at all dominated by the turbulence of the liquids itself, but much more about the little local flows around these
Right,
particles.
right, right, right. Well, to the sugar example, where you're basically introducing new solvent to the surface of the sugar in that case. One way to do that here to introduce new water, if you want to think of it that way, to the surface of silica is to somehow
Mhm.
disrupt that surface, the bed of silica.
Exactly. Yeah. So you're going to have a little boundary layer that sits just around that little coffee particle, and you're going to have a diffusive process of compounds dissolving into the bulk liquid, and whatever flows are going around the particle will disrupt that little boundary layer.
If we were to think about this, then that pore height, as we know now, changes the energy of that liquid hitting that interface.
Exactly.
If we increase the pore height, we increase the energy. What is the effect on the bed?
So the bed is going to be disturbed more and more as you get more momentum coming down, as you have more energy coming from that liquid jet. Um, so there's again a balance between sedimentation, like gravity is trying to pull all these particles down, and then you have whatever energy you provide that can help with stirring things up. And so that's going to give you some like clean, let's say, low concentration liquid between the coffee grounds. And that's exactly what then enhances the dissolution process.
As you can see now, I am with child in my lap. Sorry to bring
That's
our
right.
yeah. So okay, so I want to before he completely loses his mind here, I want to I want to get to ask the serious questions here. So the in order to get the so-called avalanching, which
Hmm.
is which is the effect where the liquid that you're pouring is so disruptive to the bed that it disrupts the bed all the way to the bottom. In other words, you
That's
get to
right.
the bottom of the cone.
Exactly.
And when that happens, you can think of it as what, like a convective flow going backwards up the side of the cone, and these particles maybe start to float, fall into the cavity. Is that how you think of it, or they just tumble because of gravity?
Sure. Yeah. So now I see where you're going with the previous question. So as you get more and more energy coming in from your liquid jet, you basically start digging deeper and deeper down into this granular bed um, to the point that you reach all the way to the bottom. So then you have coffee grounds, solid particles on the side of your coffee cone, but right in the middle, you're digging a hole. Uh, and you can imagine that this is an unstable situation because all these like dense particles now want to sink down to the bottom of the cone. And so that's an avalanche effect that suddenly this instability kicks in. Then you have all these particles that are sliding in, yeah, from the side of the cone, and then they meet this liquid jet again, where they get resuspended. That they
Get
basically get
brought
pulled
back
up
up.
right from the middle. They come back up, and then you see particles that will settle again at the top on the side of the cone. So that's where you see accretion.
You're going to observe this in certain bed depths. Is it true that
Mhm.
you'll observe this in all bed depths? So if I use 20 grams of coffee rather than the 10 that you used, would I still necessarily see avalanching?
Yeah, that's a really great question. So we've only looked at this in the context of pour over coffee, but this is actually a really important question when you look at erosion for soil, or for example, like a waterfall that's falling down and digging a hole behind a dam, for
Yeah.
example. And so yeah, like we've of course not studied this in great detail, but yeah, the more energy you have, the more of those solid particles you can erode away. Um, and so yeah, that is yeah, something that needs more study, I think.
The challenge, I guess, for the coffee person here is that when they see a 10-gram bed in a V60, what they're thinking is, well, that we might brew something that size sometimes, but more often than not, we're using more coffee than that. And so this avalanching effect where the water gets to the very bottom of the cone is still happening, but it's happening more at that sort of like at some arbitrary depth in that bed. It's still you're still disrupting the bed in a 30-gram cake of coffee. It's just not
Mhm.
necessarily hitting the bottom of the cone, right?
We found that you actually don't need that much energy to go all the way down to the bottom.
Oh, is that right?
Yeah, that's right.
So how much energy is not that much energy? What are the
So
conditions?
I think we already see that if you lift up the kettle to like 10 centimeters,
Yeah.
that like depending on the radius of the jet, of course, but you can already see that the density is lowering at the bottom of the cone.
Oh, that's very interesting. So that gets kind of to figure seven, which is I'd say the figure that people really cared about. Is this what the media got excited about as well? If was figure seven?
I don't know. I mean, it all links together, I guess.
Yeah.
But yeah, I
Well,
think
yeah.
for me that was certainly very interesting. That I mean, as you go to 10 centimeter, you already see it happening, and then as you go to 20 or 30 centimeters, then actually kind of plateaus.
Yeah.
So yeah, people ask like, oh, should I hold it up like even higher, like all the way above my head? And then I'd say like, not really, because then it's not going to make much of a difference anymore.
I did want to do a little bit of quick math, back of the envelope math here. So I was thinking about this 1.6% TDS, which is what you've managed to achieve at most of these different pouring conditions. When you're using 150 grams of water, gives you about 130 grams of material in the cup because the bed absorbs some, right? And then of that, that shakes out to be, I don't know, roughly 20% extraction yield. So that's the solvated mass divided by the dry mass of coffee that you use. And I think that's about right for the coffee people. This is a pretty representative extraction. This is what you would expect to see in a cafe. In figure seven, there's basically pour height versus extraction yield. And you can see
Hmm.
that if you have a thick jet, in other words, a fast flow rate, a lot of water moving into that bed, and you hold
Hmm.
it at, relatively high position. I mean, you hold it at 50 centimeters. 50 centimeters is pretty high. But
It is, yeah. You need a ladder.
yeah, 50 centimeters is pretty high. But let's say you held it at, 20, a foot above the, 30 centimeters above the bed, which is reasonable.
Hmm.
You can see that extraction yield continues to go up and up and up with the thicker jet. But if you use a thinner jet, so a slower flow rate, it seems like height doesn't really matter all that much.
Yeah, that's right. That's right. The flow rate there is much slower, and so you get more contact time between the grounds, and
Right.
so this is a really crucial parameter.
Yeah.
So
Well, that's it.
basically, like tip number one is like take it easy and go slow.
Yeah, go slow, right? Yeah, because if you don't want to have to try and pour from 50 centimeters above the V60, uh,
Hmm.
which maybe that's the conclusion. If you don't have a fancy gooseneck that goes slow, maybe pour from a high distance. I don't really know about that. But one of the critical things that I wanted to uh, mention here is that I saw some people discussing this on Instagram actually, and they were sort of I don't want to say negative about the result, but they sort of felt like advocating for pouring fast and high just to agitate the coffee bed was sort of going against the grain of what a pour over is because it's agitating it so much that it's basically like a suspended slurry rather than a liquid flowing through a compacted bed. And it seems like that's probably about right from the physics perspective, right? It's if you pour that with that much force, that all of that coffee is going to basically lift up.
Yeah, I think one of the other things I read, which I kind of agree with, is that if you go really high, then you have a chance that things get really messy,
Yeah, yeah,
because
splashes, right?
basically things start sloshing and splashing at some point, right? And so that's why, I mean, the first recommendation is just, like pour, more slowly so that you get more contact time between the grounds and the water. and also avoid that breakup of the droplets. And if it does start breaking up really quickly, then yeah, then lower it down again, right? So like if anything, this breakup is much more important than the height of the kettle itself.
In the notebook that sits next to your coffee making apparatus, you mentioned that you've been keeping track of data over the years. And in this paper, you mentioned that by doing all this nice work, that you can actually, in principle, reduce the amount of coffee that you use because if you do control either flow rate and pour height, or separately, you just pour slowly, you're able to elevate extraction yield. My question is, do you see this played out in the data in your lab notebook? Do you see people actually now using 10 grams instead of 12 grams and pouring in some way, pouring in a way that helps them get the same TDS?
Yeah, for me, yes. Yeah, so I always lose like 20 grams because I guess I'm a coffee addict, and so I always take a
You
double
you
shot.
need it.
But yeah, I do go down to like 20 grams. Sorry, from 20 to 18 or so. And yeah, I think it's certainly worth trying, and and I would recommend people at home to just give it a shot. And when you do an experiment, then I always say do two experiments and compare. It's
Yeah, you got to go one way and the other way to make sure, right? It's like,
exactly.
yeah, it's, I think one of the criticisms, of course, that I receive as well is that if you just report TDS, you're not really talking about that is a quality of coffee. It's the strength of coffee, but you're not talking about flavor profile. And of course, you're changing contact time by pouring slower and you're doing all this other stuff. And the cups are going to end up tasting different. So the central, I think the thesis here is, yeah, this ups TDS for sure. Now, with this knowledge of what you're doing, having this impact on this granular bed, now you need to figure out, can you do it reproducibly and do you like it?
Yeah, exactly. I think, a next set of experiments that would be really interesting is to see if we can actually reduce the amount of coffee beans that we need, and then at the same time maybe tune different flavor profiles
Yeah.
to see if we can yeah, like modulate this experiment in one way. And then there's also a big difference on whether you're making coffee at like a really big scale or coffee at a smaller scale. And so then yeah, the idea here is that, in principle, if everyone in the world would use 5% less coffee beans,
Oh, that's a big difference.
that would be a huge difference,
Yeah,
right?
that's a big
So,
difference.
and so yeah, maybe a little bit of flavor is worth it.
Yeah.
But at the same time, yeah, I don't know. This is very personal, and so yeah, I will leave that to yeah, everyone is their own expert in that sense.
Well, I'm telling you, I'm looking forward to seeing your next paper on the topic. I'm going to learn from you on how to measure flavor because it's something that's plagued my lab for a long time. Is this idea that flavor matters, but it's something that's very difficult, and I don't like collecting human data. Human too hard to work with, right?
Yeah, so actually, we did consider doing a panel as well for this, but then that means you have to involve human subjects in your research, and that involves a lot of
That's a mess.
paperwork.
It's a mess.
Yeah, it can certainly be done. It's just more paperwork, and so yeah, for this first part of this story, I think it's nice to open up this conversation, and then yeah, the best thing is to just try it yourself.
Well, I think you've neatly put a bow on it there. That's exactly what I recommend to do as well. Thanks for talking to me about this. The podcast benefits tremendously from having real authors of these real papers come on. And one of the concerns that I had when I was thinking about changing up and going with authors rather than coffee professionals was that I wouldn't be able to give like, sometimes we get into these papers and there's elements of them that are limited or not that good or poorly thought out, and I wouldn't be able to give that feedback. This paper doesn't really have that, so this one's an easy one. I'm expecting to see like later on in the year as we progress that I'm inviting people and actually have to be a little more critical about some components of it. But that this one definitely did not. So first of all, thanks for writing a thorough paper. It's really nice to see that, and thank you again for joining us in the pod. It's really a pleasure.
And I say thank you. I mean, thanks for organizing, but also just thanks for, yeah, making science accessible and, yeah, getting that interest out there. I think that's just so important. yeah, just for yeah, kids going to school right now, for our families, and just for yeah, the world as a whole.
Yeah. Yeah,
Yeah,
we need it a lot right now, that's for sure.
stay curious.